Hi everybody, and welcome to our video, which is going to be the review of our Chapter 2 test. So this is for anybody who was assigned to watch this video to do the review so that you have a better understanding of some of the answers to the questions that you may have missed on the test. So basically what we're going to do is we're just going to go through this. I'll basically take the test and explain my answers to everything, so hopefully that'll help you out. So the first questions, numbers 1 through 3, determine whether or not each relation represents a function. So for the first one, that's a mapping. And I know that whenever I had a mapping, the thing that signified whether or not I had a function was that I could never have two arrows from the same element in the domain. This was like having two x coordinates, right? So an x represented above and below. So when there's two arrows coming from the B, I know that this is not a function, right? So I would say not a function because two arrows from B or from one element in the domain. Over here, the second relation, which is just a list of coordinate pairs or ordered pairs, I know that this is not a function because we said we could never have repeated x coordinates. So we said that was another sign that we do not have a function. So not a function because we have repeated x coordinates. Okay, so that's why the answer to numbers 1 and 2 would be no, or not a function. Number 3, we said when we're working with equations, the big thing to watch out for would be if we had a plus or minus radical statement, or if I had a y squared, because if I had either one of those, that would be, if I looked at the graph, it would fail the vertical line test. In this case, I don't have either one of those, so I would say that yes, this is a function, right? Because it would pass my vertical line test if I graphed it, and it satisfies any equation here without having any repeated elements in the domain. So for numbers 4 through 6, identify the domain and range of the functions or relations from numbers 1 through 3. So it says for number 4 and 5, use set notation, right? So sets always have braces on the end. And for number 6, use interval notation. And interval notation either has a parentheses or a bracket. And inside there are going to be two numbers. This is an x coordinate where the interval starts, and this is an x coordinate where the interval ends. Okay, and if I have two intervals, I would link them together with a union. So I might have something like this, right? So this would be another x coordinate, and this would be a fourth x coordinate there. But let's look at this first. So set notation to identify the domain and range of this mapping. And so I know that with a mapping, I have two columns. This first column is the domain, and this column is the range. So my elements in my domain are A, B, and C. And I want set notation, not set builder notation. So my domain here is just the elements of the bubble on the left up in the mapping. So A, B, and C. And my range, which I can just abbreviate with a capital R, are all the elements here. So -3, 0, and 4. And I just list the elements with a comma in between. Now I can't use set builder notation here because if I were to say something like with my range, y values such that y is between -3 and 4, what that would be saying is that all of the values between -3 and 4, so numbers like -2, -1, 0, 1, 2, 3, 4, those would be all represented. And here I know that those numbers like -2 and -1 are not part of my range. So that's why I can't use set builder notation. But set notation is just listing the elements. Same thing with number 5. If I wanted to use set notation to represent this domain and range of this relation, remember domain is all the x coordinates. So since these are repeated, I just have to list them once. So my domain, elements of my domain are -1, -2, or I'm sorry, -3, -2, and -1. So I can list them out, -3, -2, and -1. And then my range is going to be all my y coordinates, -1, 0, 1, 2, 3, and 4. So -1, 0, 1, 2, 3, and 4. Okay, so that's all my domain, and that's all my range for that second relation. Now for the third one, it wanted interval notation. And so looking at this equation here, my function, immediately I see that this is a fraction or a rational function. So I know I don't want to have a 0 in the denominator because that would be undefined. So immediately I know my only restriction on my domain here is that x cannot equal -3. And the reason for that is if I put a -3 in here, I'd get -3 plus 3, and that would give me 0. Okay, so now I know that my domain is all elements of the real numbers, so all real numbers except for x equals -3. And I thought that'd be easier to write in interval notation because we would just use -infinity to -3. We'd put a parentheses by the -3 because it's not included. Then we would union that with the interval of -3 to positive infinity. Okay, and so that would be my domain here. Now the tricky part with this is that the range would be, we'd want to say all real numbers, but there would be a limitation. So the way I would determine that is I would open up, I would go to Desmos, and I would open up my calculator here, and I would plug in that function, or you could use your graphing calculator if you'd like. So we want to put in x squared, I think it was -9, divided by, and we could put x, was it x minus 9 or plus 9? Let's double check real quick. Where is that notebook? There we go. It was -9 then over x plus 3, okay? So I'm going to put in x plus 3. Okay, so now let's look at this graph. If I'm looking at this, it's a line, right? So I'd be tempted to say that my domain is all real numbers, but I notice that when I get over here to, if I trace this, when I get to -3, it should say undefined, right? So there's no x value, right? The x value of -3 can't be in my range or my domain. So then looking over to the corresponding y coordinate that would go with this -3, there isn't one. But if I looked right over here, I know that corresponds to -6. So right there, there's a hole in my graph at -3. So I know that that point is not part of this graph. So I know that that -6, which would be the corresponding y coordinate, is not part of my range. So just like I put an open interval, the interval skipped over -3 for my domain, same thing is going to happen with my range. So my range is going to be from -infinity to -6, and I'm going to union that with -6 to positive infinity. So that would be my domain and range for number 6. This was probably the problem that most people had a mistake with. So, but everything else people generally, was maybe their algebra or arithmetic that tripped them up. But that, I think, was probably the hardest concept-wise. So let's move on to our f plus g of x. So we have f of x, we have g of x. And remember when we did these examples in class, I said the easiest or best way to do this is to first write these out in parentheses, because I'm f plus g of x. Remember, that's f of x plus g of x. So you take f of x, put it in parentheses, then you take g of x, put it in parentheses, and then write it without the parentheses. So 3x squared minus 1 plus 2x minus 4. I don't have to change anything here. And so now all I have to do is combine my like terms. So in this case, I have -1 and -4, and I'll combine them together. So I have 3x squared plus 2x, and then I combine -1 and -4. That gives me -5. Now, that doesn't seem like there wasn't much to change with that parentheses, but now I'll show you why it's a good idea to write it with parentheses. Because in this next one, which is the one that almost everybody got wrong, when I write this in parentheses, what I'm noticing is that I'm subtracting this whole function g of x. So when I rewrite this without parentheses, I'm subtracting 2x, and I'm subtracting -4. So minus -4, which would really be +4. And so now, again, all I have to do is combine my like terms, which are the constant terms here, and I would get 3x squared minus 2x, and negative 1 plus 4 is plus 3. Almost everybody who didn't write this with parentheses or didn't catch this subtracting the negative 4 had the minus 5 here again with number 8, so that's why we got that one wrong. Moving on to f times g of x. Again, I'm going to write this in parentheses. 3x squared minus 1 times 2x minus 4. And again, this is nice when it's in parentheses because immediately I can see that this is FOILing. So I'm going to multiply my first terms, 3x squared times 2x. 3 times 2 is 6. X squared times x is x cubed. Then here I would do my outside terms. So 3x squared minus 4. So that's going to be minus 12x squared. 3 times negative 4 is negative 12, and then the x squared carries along. Now my inside terms, negative 1 times 2x, so that's negative 2x. Now my last terms, negative 1 times negative 4 would be positive 4. Okay, so that one's already in the appropriate form, and so I'm done with that one. Now, f over g of x. So again, first things first, I want to write this with parentheses, so 3x squared minus 1 all over 2x minus 4, and this is where most people stopped. But remember, since I have a fraction, what I have to say is that 2x minus 4 cannot equal 0 because I want this to be a defined statement. And so what I want to say is what x cannot equal. So 2x minus 4 cannot equal 0, so that means 2x cannot equal 4. And divide by 2, and you get that x cannot equal 2. So that had to be part of your answer, and that's why I would have marked this question wrong for you. What is the value of f plus g of 2? So if I wanted to do that, I could just take f plus g of x and plug in 2. So here I would say 3 times 2 squared plus 2 times 2 minus 5. So 3 times 2 squared. The 2 squared is what needs to be done first. So I have 3 times 4 plus 2 times 2, which is 4, minus 5. So 3 times 4 is 12. 12 plus 4 minus 5. And 12 plus 4 is 16. 16 minus 5 is 11. So I scroll down here, and my answer is A, because I had f plus g of 2 was 11. Now, what is the value of f over g of 2? I was trying to make that one easy because you would have seen right here that x cannot equal 2, so you would know immediately that that's undefined. Okay, moving on. Page 2 is another one that had some trouble for some people. So first of all, what's the value of f of negative 2, interpreting from this graph? So that is saying f of x, right? So x equals negative 2, and the f of x is the y value. Remember we said y is the same thing as f of x. So what is the y coordinate of negative, where the x coordinate is negative 2? And that would be right here. So our answer is D, negative 2. How many, and the question on your test is actually how many y-intercepts, not x-intercepts. How many y-intercepts does f of x have? So y-intercepts are where the graph crosses the y-axis. And so in this picture, here's my y-axis. And so this line here, how many times does the graph cross it? Only this once. So we only have one y-intercept. So my answer there is A. Now use interval notation to identify the domain and range of f of x. Remember, interval notation is either parentheses or brackets, and it's got just 2 points in here, 2 x coordinates, an endpoint, and 2 endpoints of the interval, basically, and union it if we have multiple intervals. So my domain should be relatively easy because these arrows represent negative infinity here, right, because it's going down and to the left. And over here, this represents positive infinity on the x, negative infinity on the y, because it's going off to the right but down. So it goes from, my x coordinates go from negative infinity to positive infinity, so that's all real numbers. So I could write that as negative infinity to positive infinity. So that's easy to find the domain. The range, however, remember we said there's a couple ways you could think of this. One way was to draw a box enclosing the function. And so here, I can't close the box because the arrows go off forever. So I know that it goes down to negative infinity along the y-axis. And up to the top, the highest y value I have is 2. And that's included because it hits 2 on the y-axis if I draw this box. So my interval notation to represent the range is negative infinity to 2, and I put a bracket around the 2 because 2 is included. So that's the highest y value that I get. On which interval is f of x increasing? So I just want to know where it is increasing. And remember, we always read increasing, decreasing, or constant from left to right. So it starts increasing over here. Even though the arrow is pointing down, as I move from left to right along the function, it's going up until it hits this point right here. And then it starts coming down, so it's decreasing there. Then at this point, it changes and starts to go back up again until it hits right here. And then it switches and starts coming back down. It passes through this point, negative 8, 0, but that doesn't switch anything. It's still been increasing from here all the way through there, and it increases through the origin too. So those aren't endpoints of my interval of where this is increasing. It's increasing through that point, just like it's increasing through all these other points that aren't labeled. So technically it's increasing from the interval of negative infinity until negative 6, and then from negative 2 to 2. So that's the intervals on which f of x is increasing. So it should read negative infinity to negative 6, and, or you could say union if you wanted to. I accepted that notation. You could also say from negative 2 to 2. Okay, and remember, these are parentheses around these intervals because at these points, it's neither increasing nor decreasing. That's a relative maxima because it's at the top of the hill, and that's a maxima is where it switches from increasing to decreasing. Down here, that's a relative minima because it's switching from decreasing to increasing. So at that exact point, it's neither increasing or decreasing, it's switching. Okay, so that leads to our next question, number 17. Identify all the relative maxima of f of x. Now, I took the maximum value, if you said that, because technically we said the relative maxima are points. They're the points at the top of the hill, basically, where it's switching from increasing to decreasing. But if you gave me the maximum value and said 2, y equals 2, right? Because remember, the y value or the f of x value is the maximum value of that function. I took that, but I also just said, hey, it could also be these points. So technically, our 2 points that are our relative maxima here are negative 6, 2 and 2, 2. So if you said that the y equals 2 was your relative maxima, I took that. But if you also said that it was the points negative 6, 2 and the point 2, 2, I took that as well. Okay, working over here, number 18, does the graph below represent even, odd, or even function, odd function, or neither? Number 18, right away as I look at this, first of all, it fails the vertical line test, so it's not even a function, so that's how I would know it would be neither. Another way to tell that is because I know that when a function is even, it's symmetric to the y-axis, and when a function is odd, it's symmetric to the origin, right? Because I remember that from O, odd, origin, O. So that's how I remembered. That was my mnemonic device to remember that. And here, simply, it just wasn't a function. So my answer to number 18 was neither, extra I there, neither even nor odd. Now, algebraically, and we could always check this answer by plugging in its graph, but algebraically, I had 3 columns that I needed to compare. I had f of x, then I had f of negative x, and then I had the opposite of f of x. And if these first 2 columns matched, then it was even. If the second 2 columns matched, it was odd. And if none of them matched, it was neither. So first of all, f of x is 3x to the 5th plus 5x. Now f of negative x would be 3 times negative x to the 5th plus 5 times negative x, right? I'm just plugging in negative x for x here. Negative x to the fifth is negative x times itself 5 times. So when I do a negative times a negative times a negative times a negative times a negative, right? A negative times itself 5 times, or any odd number of times, will end up being negative. So this is going to be negative 3x to the fifth, because it'll still be a negative x, and the negative times a 3 becomes negative 3. Over here I have 5 times negative x. That's really negative 5x, right? So that's f of negative x. Here, okay, so first of all, I see that these first two columns don't match, so it's not going to be even. So now I take the opposite of my function, which is 3x to the fifth plus 5x. The opposite of that, distribute the negative sign, becomes negative 3x to the fifth minus 5x. And if you look at this, these two columns match up, so that means that this f of x is an odd function. Okay. Moving on to number 20, f of negative 3, right? So f of x, and so x is negative 3. So this is a piecewise function, and it's telling me which one to plug it into. So if x equals negative 3, which one do I plug it in? Is negative 3 less than negative 10? No, so don't plug it in there. Is negative 3 greater than negative 3? Nope, don't plug it into that one. Is negative 3 between negative 10 and negative 3 included, right? So it's less than or equal to negative 3? Right, it's this one, because it's equal to negative 3. So I'm plugging it in to this part of this piecewise function. So negative 3 squared minus 9. Negative 3 squared is negative 3 times negative 3, which is 9. 9 minus 9 equals 0. So my answer is B. Good. Moving on to our third page, match each of the following parent functions with their graphs below. So I know from studying my packet or from simply plugging these into my calculator to see which ones of these graphs it matches below. I know what these graphs look like. First of all, this one is a parabola. We know that because it's x squared. So I can just remember this from our packet of the family of functions. This absolute value is shaped like a V, and x cubed, I know that it's one goes up and the other end goes down, and then this cube root looks something like this. It looks like the inverse of x cubed. Right, so if I'm looking through here at my different graphs, immediately I would put B in for the V for the absolute value. Over here, this looks like x cubed, so it's C. And then as I move down, this is clearly the cube root, which was D. And then my parabola was A. So this one should have been easy if you studied your family of functions, just their basic graphs, and to recognize how to match them up. Okay, moving on to the next page, another matching. E, F, G, and H. So I'm looking at this. The parent function would be the absolute value function, so I know all of these should be a V. Now there's a few ways that I could go through this. First of all, I could check and see what's happening here. With this negative sign out front, that means the V should be going down, right? So whenever I have a negative out in front, that means it's reflected over the x-axis. So I know F, G, and H, they're all opening down, so E is the only one that's opening up. So check your graphs here. Are there any that are opening up? This one here. So immediately I know that one's E. And I got that one. I can cross it off my list. Okay, F is opening down, and then there's a negative 2 inside the absolute value bars. So whenever we said it was inside the function, as opposed to this plus 3, which is outside, the inside moved it left or right. So which one of these opens down and is moved to the right too? Because remember, it's x minus h. So I look over here, and there's two of them that look like this. There's two of them that are opening down, this one here, and this one here. This one is moved to the left, or I'm sorry, moved to the right, and then this one is moved to the right, but it gets skinnier, right? It's skinnier than these other three. And so I know that that means there's also a vertical stretch going on here. So I look back up here, and so I know that F doesn't have a vertical stretch. So this is the one that's moved to the right, doesn't have a vertical stretch. That's F. Then down here I see H has the A equals negative 2 out in front, so that means there's a vertical stretch. So I know that this one is H. And then I double check and make sure that this last one is moved over 2 to the right and up 3 and opens down, and so that fits with G. So that's how I would recognize all of these transformations here. And then our last page, evaluate each of the following expressions given the greatest integer function g of x equals the greatest integer of x plus 2. So what I'm doing with each one of these is plugging in g of x, so g of 1.6. So I take the 1.6 and plug it in here and add 2. Now off to the side, remember, this is a little note that I think some people forgot. If I had something like this, where I had the absolute value of negative 7, when you take the absolute value of something, what you're doing is you're changing the sign of what is inside there, if it's negative. So the absolute value of negative 7 is 7, right? We were used to that. So if I gave you something like, what's the absolute value of negative 7 plus 2, you would say the absolute value of that is 7, and then you add on 2, and so you get 9. So here I'm taking the greatest integer function of 1.6. Remember, the greatest integer function was defined as the greatest integer that was less than or equal to x, right? So it's got to be an integer, and the integers are the positive and negative whole numbers plus 0, right? So 0 is also included. And less than or equal to, remember, less than is always the number that's on the left on the number line. So for example, if I had here negative 2, negative 1, 0, 1, and 2, 1 is less than 2, 0 is less than 1, negative 1 is less than 0, negative 2 is less than 1. So in this case, the greatest integer that is less than 1.6 is 1. So I have 1 plus 2 equals 3. Here, the greatest integer that is less than or equal to negative 2.3. Remember, these are all my integers on my number line, and it's always the integer to the left. So if I have negative 2.3, that's right about here, and the integer that would be to the left of this on the number line is negative 3. So this is negative 3 plus 2, which is negative 1. Down here, the greatest integer that is less than or equal to 4. 4 is an integer, and so remember it's the equal to part. So it's going to be 4 plus 2, which is 6. Okay, so remember, you should have only integer answers here because of the greatest integer function. So when I have my decimals here, it changes this number inside to an integer, basically. And the integer that's changing it to is the one that is less than or equal to that number. So just like in absolute value, it changes this number to the number that is the distance away from 0 on the number line, or basically changes it from negative to positive. And so that's why here, just like we changed the number, we're changing this number here to an integer like that. Okay, now list the transformations to the parent function of f of x equals x squared represented by the following equations. So we could write out our a, b, h, and k if we wanted to. And here we know that we have a is negative 1, b is just 1, so we don't really have to worry about it. H, it's x minus h, so h is 5, positive 5, because x minus 5, so x minus h equals 5, and k equals 3, so that's because of that plus k on the outside. So if it's negative 1, that is a reflection. Let's write all our answers in green. That is a reflection over the x-axis. Okay, so that's one transformation. H equals 5, so that is a shift 5 units to the right along the x-axis. And K is 3, so that is a shift 3 units up along the y-axis, or vertically. So those are my 3 transformations represented by these 3 parts of the equation. So basically, number 24 was giving you the equation and wanted you to write out something like the bullet points here in number 25. And now number 25 was the reverse. So it was telling you these different transformations that were happening, and it wanted you to write just one equation, an equation in transform form. So some of you wrote a separate equation for each one of these, but I wanted you to put it all together and just write one equation at the end. So the parent function is the square root function. So I know that what I'm trying to fill in here is f of x equals a times the square root of bx minus h, and plus k is on the outside of that square root. So now try to figure out what everything is. The graph of the parent function is shifted 3 units to the left. So 3 units to the left means h equals -3, because it's 3 units left, left is negative. 7 units up, that means k is +7, because k represents the vertical shift. The graph of the parent function is reflected over the x-axis, so that's a, because remember, a was over the x-axis, b would have been a reflection over the y-axis. So if it's a reflection over x, that means a is negative. Now it says the graph of the parent function is vertically stretched by a factor of 2. So again, that's a, and so now I know that a is -2. So to fill in my function here, my equation, I would say f of x equals a, which is -2, times the square root of, there's no b to worry about because we didn't talk about any horizontal reflection or stretching or compression. So just x, and now it's minus h, so minus -3 is really +3, and then plus k on the outside is +7. Okay, so hopefully this helps you catch all of your mistakes from the test. Hopefully you've taken good notes and this helps walk through it, or it was a refresher on how to approach this. And we will pick up some notes and start the next chapter, chapter 3, tomorrow. All right, have a great night.